In physics, assuming a flat Earth with a uniform gravity field, and no air resistance, a projectile launched with specific initial conditions will have a predictable range. The following applies for ranges which are small compared to the size of the Earth. For longer ranges see suborbital spaceflight. The maximum horizontal distance traveled by the projectile, g, the gravitational acceleration usually taken to be 9.81 meters per second too near the Earth's surface, I, the angle at which the projectile is launched, v, the velocity at which the projectile is launched, yo, the initial height of the projectile, d, the total horizontal distance traveled by the projectile. When neglecting air resistance, the range of a projectile will be, if is taken to be 0, meaning the object is being launched on flat ground, the range of the projectile will then simplify to ideal projectile motion. Ideal projectile motion states that there is no air resistance and no change in gravitational acceleration. This assumption simplifies the mathematics greatly, and is a close approximation of actual projectile motion in cases where the distances traveled are small. Ideal projectile motion is also a good introduction to the topic before adding the complications of air resistance. Derivations equals, 45 degrees goes the farthest. This is due to the nature of right triangles. Additionally, from the equation for the range, we can see that the range will be maximum when the value of is the highest. Clearly, has to be 90 degrees. That is to say, is 45 degrees. Flat ground. First we examine the case where is 0. The horizontal position of the projectile is in the vertical direction. We are interested in the time when the projectile returns to the same height it originated. Let Tg be any time when the height of the projectile is equal to its initial value. By factoring. Or. But T equals time of flight. The first solution corresponds to when the projectile is first launched. The second solution is the useful one for determining the range of the projectile. Plugging this value for into the horizontal equation yields. Applying the trigonometric identity, if x and y are same, allows us to simplify the solution to. Note that when is 45 a degree, the solution becomes uneven ground. Now we will allow to be non-zero. Our equations of motion are now and. Once again we solve for in the case where the position of the projectile is at 0. Again by applying the quadratic formula we find two solutions for the time. After several steps of algebraic manipulation, the square root must be a positive number, and since the velocity and the cosine of the launch angle can also be assumed to be positive, the solution with the greater time will occur when the positive of the plus or minus sign is used. Thus, the solution is solving for the range once again. To maximize the range at any height. Checking the limit as approaches 0. Angle of impact. The angle I at which the projectile lands is given by. For maximum range, this results in the following equation. Rewriting the original solution for I, we get. Multiplying with the equation for 2 gives. Because of the trigonometric identity, this means that I plus I must be 90 degrees. Actual projectile motion, in addition to air resistance, which slows a projectile and reduces its range, many other factors also have to be accounted for when actual projectile motion is considered. Projectile characteristics equals, generally speaking, a projectile with greater volume faces greater air resistance, reducing the range of the projectile. This can be modified by the projectile shape. A tall and wide, but short projectile will face greater air resistance than a low and narrow, but long, projectile of the same volume. The surface of the projectile also must be considered. A smooth projectile will face less air resistance than a rough-surfaced one, and irregularities on the surface of a projectile may change its trajectory if they create more drag on one side of the projectile than on the other. Mass also becomes important, as a more massive projectile will have more kinetic energy, and will thus be less affected by air resistance. The distribution of mass within the projectile can also be important, as an unevenly weighted projectile may spin undesirably, causing irregularities in its trajectory due to the Magnus effect. If a projectile is given rotation along its axis of travel, irregularities in the projectile's shape and weight distribution tend to be cancelled out. See rifling for a greater explanation. Firearm barrels for projectiles that are launched by firearms and artillery, the nature of the gun's barrel is also important. Longer barrels allow more of the propellant's energy to be given to the projectile, yielding greater range. Rifling, while it may not increase the average range of many shots from the same gun, will increase the accuracy and precision of the gun. See also, trajectory of a projectile.